She wins. Okay, great. Next speaker is Schramm.
Thanks, Pablo. So my talk is going to be about fast spectral algorithms from sum of squares analyses. So let me just write out the title. Okay, and one really nice area of development in sum of squares recently has been a bunch of sum of squares algorithms for what David termed machine learning problems. Okay, so this is stuff like, tensor decomposition and tensor completion, and all kinds of learning problems like community detection, dictionary learning, etc. Right? And something really, really nice about these SOS algorithms is that they're really, really strong. So they solve harder problems. Meaning, like, for many of these problems, there's some parameter like sparsity. And as you ratchet up the sparsity, the problem gets harder. So like, if the problem is super, super sparse, you can solve it pretty easily. But then as you increase the rank, it gets more difficult. And sum of squares can achieve algorithmic guarantees for much higher ranks. So sparsity is just one example. I just thought that would be a familiar thing for people. And then also, they're really robust. So in the sense that for learning style problems, oftentimes you're trying to learn some distribution, okay? And the more samples you have, the lower your signal to noise ratio will be, right? But there's this cost to gathering more data. So sum of squares lets you work in settings where there's much more noise than previous algorithms have allowed you to do. Okay, so this is really nice, and you can think of this as a proof of concept that these problems are in fact in polynomial time, okay, which is really awesome because we didn't know that before. But there's a small drawback, which is this is pretty slow. Okay, so like, what do I mean by slow? Like say that we're thinking about some learning problem, like maybe dictionary learning. So you're solving an SDP in n to the maybe 6 variables. Okay, so sometimes you don't know that it's 6, but sometimes it is 6, right? And so you have n to the 6 variables, and n is like the number of features. So like maybe if you're trying to learn something about photographs, okay, the number of features is like the number of pixels in your photograph. So let's like make a like a pretty modest estimate that maybe this is like 10 to the 4. Okay, so then like 10 to the 4 to the 6, that many variables, and then you solve an SDP. That's like a really burly AWS instance, right? Like that's not something that we can really hope to run. And so one would say, well, maybe you can get something additional out of these SOS algorithms. Maybe you can take the insights that were developed when analyzing these algorithms and transfer them into spectral algorithms or something more lightweight that you can actually hope to run in practice. Okay, so in fact, there have been a couple of works about the subject where you take an SOS analysis and you get from it a fast spectral algorithm. Okay, and by fast here I mean like definitely sub-quadratic time and sometimes even near linear time. And let me just list a couple of papers. So the first kind of work on this topic was by Sam and myself and Jonathan Shih and David Stoyer in 2016 for the average case tensor decomposition. And some other problems. And then there's a follow-up work by Montanari and Sun from the same year about tensor completion. So both of these works are based on sum of squares analyses that use primal dual analysis, right? And so you're doing some kind of spectral primal dual analysis. In these two works, you can sort of bypass that and turn that into a spectral algorithm yourself. So I'm being like super vague right now, but essentially these work through the dual, okay? But today I'm going to focus on a newer work which is joint work with David, that does robust tensor decomposition. Okay, and kind of the difference between these two works and this work is that here we're really working in the primal space. Okay, so it's kind of like a new strategy for SOS speedups. Probably if I draw down here, it's too low to see. Okay, so I'll move up here. So let me just outline very like bird's eye view what the strategy is here, and then I'll say more precise things. Okay, so for these tensor decomposition problems, the best sum of squares algorithms solve an SDP of the following thing. So I have some input tensor T. And what SOS will do is it will solve a maximization problem, max xt, where x is some matrix. Right? And then there's going to be a bunch of other constraints.
What dimension is tensor? Does it matter?
For now, like, I mean, no, actually, this is true for every order tensor that we know. But for now, like, let's say it really doesn't matter because we're in such an abstract place that it could be any order. So okay, so we have this SDP, and we're trying to find a point that's correlated with T and satisfies all these constraints. Or you could also think of this as we have some set of convex constraints. And we have our input tensor T, and we're trying to project T into the intersection of all of the constraints. Okay, so this is what the SDP is doing. The SDP computes its projection, right? And then what we do is we take this projected point and we apply a rounding algorithm. And as we're analyzing the rounding algorithm, we'll use all kinds of properties of these convex sets that we know that we're in the intersection of, right? So this is like, what always happens, basically. And like the really expensive step was this step, right? Where we said, okay, we really care about all of these convex constraints, and we're going to compute the projection into their intersection. But actually, ultimately, in the end, maybe we didn't use properties about every single one of these constraints when we analyzed the algorithm. Okay, maybe we could have gotten away with much less. And also, maybe we didn't have to just directly compute the projection into the intersection. Maybe we could have done this in an iterative fashion that would have been less expensive. So that's exactly what we do. So what we do is we choose some key constraints that were important in the analysis of our rounding algorithm. So maybe just these two. We take our same starting point T. But now what we do is we compute the projection iteratively, right? So maybe we first compute the projection to the nearest point in this constraint. This is point 1. Okay, and then we project down to the next second point, right? And then what we're going to do is we're just going to hand off to the same rounding algorithm. And because we more or less satisfy all of the properties that we used when we analyzed the rounding algorithm for the SDP solution, our algorithm is still going to work. Okay, so this is a way to avoid the SDP solve because each of these projections are just going to be like fast sum of spectral algorithm projections.
Yeah. So before you go, so can you say why this is so? Like, do you have a extra information about normal fixes? Because like x minus t squared has this inner product, but it also has the normal fixes squared. And then how is that? How is this projection? How is maximizing xt?
No, x is the thing that x is our variable of our program, right? So we can constrain the norm of x however we want.
The projection is x minus t squared. So and that gives you x squared.
Okay. It's not like I'm not sure that you could formally, like maybe it's not like exactly formally projection, but close enough. We should maybe talk offline. So, okay. Anyway, this is like the high level overview of what's supposed to be going on. Okay. So in the remaining time, I want to tell you about the robust tensor decomposition algorithm. And I sort of took, like, when I was planning this talk, an extreme position on the accuracy and precision versus information scale. So like I'm going to try to convey as much information as possible, but it might not feel very precise. So at any point, please stop me and make me give you the details, or tell you I'll give them later. Okay, but first of all, I guess I should start by telling you what tensor decomposition actually is. So let's see. Let's do it here. Okay, so let's start with actually what is a tensor, right? So a tensor is just going to be a higher order array of numbers. So like a 3 tensor is the maximum size of a tensor that I can draw. But actually today we'll be working with 4 tensors, just because even order tensors are nice. The order is the sort of number of dimensions. And the dimension of the tensor, so we'll be working also with completely symmetric tensors, right? So I assume that each of these guys is an n by n by n array, and I'll have n of them. This is an order 4 tensor. Okay, and I'll have the entries be in the reals. And a fact that's true about tensors that sort of generalizes facts that we know about matrices is that I can write such a tensor as a sum of rank 1 tensors. Okay, and when the tensor is symmetric, I can write it as a sum of symmetric rank 1 tensors. Sorry, this should be a 4. Where the VI are vectors in Rn. Okay, and M here is the rank of the tensor. And something that is true for matrices but is not true for tensors is, or I guess something that the tensors don't do is it's actually NP hard to compute such the minimum rank decomposition in the worst case. I guess I didn't say that the tensor decomposition problem is to find the VIs or vectors that are close to them in L2 norm, or in whatever sense that you would like.
These are all symmetric tensors, right? Essentially, these are polynomials.
Yeah, so these are symmetric tensors. Actually, the algorithm that I'm talking about today can also be applied to asymmetric tensors, although in the paper it's not written up this way. But yeah, and I think the same might be true for the sum of squares algorithms if you're willing to take a hit in the degree. But yeah, let's assume symmetric tensors. I mean, this is already an interesting case.
But then, so not every polynomial can be written as a sum of sort of fourth powers of linear forms. But
That's
you're
true.
assuming that you're sort of handed one that has such a decomposition, and then you want to find it.
Yes. Yes. So computing such a decomposition is NP hard in the worst case. So this differs from matrix decomposition, which is sort of like finding the singular value decomposition. But in the cases when you can find the VIs, so in many cases of interest, you get a bonus over matrices, which is that the decomposition will be unique, right? So like in the matrix case, if I have a matrix M, say that U V transpose is like its singular value decomposition, right? It's also true that I can put any rotation and its inverse in the middle. And this is also a perfectly valid decomposition. Okay, but for tensors, this will not be the case, right? Like many times, in our cases of interest, the decomposition will be unique, and that's what makes this like important primitive in many learning problems. So this uniqueness like kind of gives you it's a nice property. So OK. Any questions about tensor decomposition?
So just to keep the time, you probably want to have signs in front of these, right? Or do you really mean sums, or you're also allowed to take differences?
Yeah, I mean, I'm allowed to put like a sign here if I want. Sure. Let's. It shouldn't change anything for today, but let's not. Let's ignore them because it will make things notationally more difficult. Yeah. OK, so this problem is NP hard in the worst case, but for specific types of tensor decomposition, for specific types of tensors, we know algorithms. OK, so OK, maybe here also you already noticed that this was average case tensor decomposition, robust tensor decomposition. Basically, there are many different ways that one could try to take the tensor decomposition problem and find like the edge of tractability. Right, so but let me start at like the very safe interior of tractability. So an algorithm that's been known since the 70s is Yonnex algorithm. Here. Okay, and let's assume that we're in the following case. So Yonnex algorithm has guarantees for the following case. So the vectors, v1 through vm, are orthonormal. Okay, so unit norm and orthogonal. So in this case, Yonnex algorithm applies. And the reason that I'm telling you about Yonnex algorithm is that this is actually this rounding algorithm that both SOS and us ultimately will pass off to. Okay. But also, it's like a really basic algorithm that's nice to see. So what am I going to do? I'm going to take my input tensor T. Okay, it's this sum of VI tensor 4s. And I want to find these guys. I'm going to think of it as a big, tall stack of matrices, like a n squared high stack of matrices. And let me, for notational convenience, call the A-B slice here T sub AB. Okay, so A and B are numbers between 1 and n. And what I'm going to do is I'm going to sample n squared IID Gaussians. Okay, and I'm just going to compute the matrix, which is the sum of the scaled slices. So sum GAB TAB. Okay, so just a random contraction. Okay, now it turns out that this TAB is secretly equal to sum over I from 1 to m VIA times VIB times VI transpose. So like, I don't want you to think about this too carefully. This is just like a syntactic fact that you can verify for yourself. But what that means is that if we look at this sum here, this is equal to the sum over the vectors now, G inner product VI tensor 2, VI transpose. So this is the n by n matrix, right, which is a sum of these orthonormal vectors with random independent coefficients. So now if I compute the singular value decomposition of this n by n matrix, I'm going to exactly recover the VIs, right? I mean, because these will be independent Gaussians, and they're not going to be the same value with probability 1, basically. OK, so then I pass off to an SVD. OK, and then I'm done. So that's the Yonnex algorithm. And it's very, very nice for the orthonormal case. There's one really serious drawback, which is that this is not at all robust to noise. OK? So let's see why. So let's say that I also want to have, I'm not given T, but I'm given T, which is equal to, or T twiddle, let's say, which is equal to T plus some noise tensor E. Okay? And okay, so like obviously I can't make E just whatever I want because then we would be in this NP-hard case. Right? So let's say that I make E, I'm going to make some pretty reasonable worst case assumption on E. So I'm also going to introduce some pretty non-standard notation here. So remember, E is an order 4 tensor. I'm going to call E sub a little square to be the n squared by n squared flattening of this tensor. Okay, so this is a block matrix. And in the A bth block, I'll put the matrix E, A, B. Okay, and similarly, I'm going to use the E sub rectangle notation, okay, which is the same thing, but this is the n by n cubed reshaping. Okay, so maybe like one reasonable assumption that I could make is I could make the assumption that the spectral norm of the square reshaping of E is its most epsilon for some small constant epsilon, right? So this is actually allows me to capture many different settings, but also it's a reasonable constraint on E to make sure that I don't get into any of these hard cases. So, okay, so suppose that this is the case. So now, because this is a linear operation, right? If I apply Jensen's algorithm, or sorry, Yonnex algorithm to T tilde, I'm going to get some over AB, GAB, T twiddle, AB, which is just the same as applying it to T and to E separately, right? So here I get the nice thing. Do you think that was us setting off the? Okay, so this is our old friend from that board over there. But here the problem is that if you use matrix concentration to bound what the spectral norm will be like of this term, it's going to be something like square root log n times the spectral norm of the rectangular reshaping of E instead of the square reshaping of E with high probability. And this guy can be as much as epsilon square root n. Okay, so if we make this assumption, there are situations in which we get a spectral norm of epsilon squared n here. And what that means is that if we want this term to dominate, this signal term to dominate the noise, we need this Gaussian to be at least root n log n, which is an exponentially unlikely event. Right. So the hope would be to be able to still handle this case.
But if your tensor is orthogonally decomposable, that's I mean, as opposed to matrix, that's a very small very small proportion of tensors are going to have this orthogonal decomposition. And if you add noise, you will probably fall into a regime where you're not orthogonally decomposable. You don't have such decomposition.
Right.
Right. So what do you do? Is the goal to find the closest orthogonal tensor?
No, the goal is to find T itself. So like the setting you should have in mind, I should have said this in the beginning, is that T is it's like the moment tensor of some distribution, okay? And T tilde is something that we got by taking the empirical moment tensor, right? And so E is some noise, and if we take more and more moments, we can control its spectral norm. But it might have some systematic errors as well, right? But still, what we want is the true moment tensor, and that should be given by T.
So how close to exact can this get? I mean.
Yeah. So let me write down the SOS theorem to start. Right. So okay. So here's a theorem. So this theorem, due to Tengyu Ma and Jonathan Shi and to David, is that in that case, so if we get t tilde, which is t plus e, and the spectral norm of the square reshaping is bounded by epsilon, then degree 6 SOS can recover U1 through UM such that UI inner product VI squared is at least 1 minus epsilon. Maybe here it's 1 minus order epsilon. Okay, so you can get pretty close.
And the VI are orthogonal as before.
The VI are orthogonal as before. Okay, so already I think this is pretty surprising because here we didn't make any strong assumptions about the noise. Like in some sense, we're in the worst case noise model, right? It's not like IID entries or anything like that. Okay, so now I'll say very briefly something about this algorithm. So the algorithm works by writing down the following relaxation. So you want to find tensor x, which is close to t tilde. Your goal actually is going to be to recover t itself. So now you put down all kinds of reasonable constraints, like you want the trace to be n, and you want the tensor to be positive semi-definite in its square reshaping. You want the spectral norm of the rectangle version to be at most 1, and a bunch of other SOS constraints, right? But now you're only going to crucially use 2 facts in your analysis. Okay, so the first fact is going to be that x can't correlate very much with e. Right, so you prove this using some sum of squares analysis, using your constraints. And then the second thing that so basically what this means is that you have to be close to t. So one more thing I should say is that a feasible solution to this program is to just plug in t. There the objective function is n, right? So what this actually implies is that x and t correlate at least 1 minus epsilon n, which is large as a fraction of the trace of x. Okay, and then the second thing that you're going to use is you're going to use that the rectangle norm of x is small. Okay, so basically what you do is you say, okay, we have some tensor that's close enough to t, right? So that if I go and I apply Yonnex algorithm to it, I'm going to recover one of the VIs. And the reason that we needed the rectangle norm restriction is exactly for this reason, right? So on average, there will be one guy that you're very close to, right? And the rest will be bounded in spectral norm. So this was very sloppy, but that's the general idea, yeah.
Just to be clear, the spectral norm constraint is implied by the usual SOS constraint.
Yes. Yes. Yeah, I just wrote it here explicitly.
And
Yeah.
when you write n, you mean m?
I do mean m. And here I mean m everywhere. I guess let's make n equal to m. Okay, so
why would that on the left exist? This the thing with the rectangle norm being less than 1.
Yeah. So if I take t itself, right, and I write down its rectangular reshaping, I get sum over I, vi tensor 3, vi transpose, right? And each of these is an orthogonal, like orthogonal to all the others, and it has norm 1. So the spectral norm of this is 1. Okay, so now I guess in the couple of minutes remaining, I'll say what we do, right? So essentially what we want to do is we want to avoid solving this SDP, but we want to still be able to produce an object X, which is not very correlated with the noise, and also has small rectangular norm. So what we'll do is the following. So in our first step, we'll take t twiddle, okay? So T twiddle is equal just to T plus E. But if we look at the inner product of T twiddle with E, this could be approximately the same as just looking at the Frobenius norm of E squared, right? Because, you know, T is maybe negligible in Frobenius norm compared to E. And here, this is a rank n squared matrix, right? Even though the spectral norm is epsilon. So this could be something like epsilon n squared, which is too much for us, right? We only want order m or n correlation. So what we do is we say, OK, well, let's look at the spectrum of T twiddle. So these are the eigenvalues. So because it's essentially a rank n matrix of eigenvalues 1 with a perturbation added to it, like a small perturbation, we know that this is going to look like this. So it'll be n eigenvalues that are close to 1, and then all of the others will be epsilon.
Spectrum of the square, the reshaping? Or?
Yeah, of T square reshaping. And what we do is we just say, OK, we don't need any of these eigenvalues, right? So we just compute the first n eigenvalues of T twiddle, and we keep those. So let's let T prime be equal to the to T twiddle square greater than epsilon. I hope this notation is clear. OK, and now what you want is you want to prove that T prime is close to T. So how do you do this? Well, let's look at the distance between T and T prime. So this is at most the square root of the rank. Times the spectral norm of the square reshaping. Right. Here I took the difference of two rank n matrices, so this is at most 2n. And here I can just use triangle inequality, right? So I compare T to T twiddle. That's at most epsilon. And then I compare T prime to T twiddle, right? So that's also at most epsilon, because I just removed a bunch of eigenvalues of value epsilon. Should I write out the triangle inequality, or everyone? No. OK. All right, so this is at most 2 epsilon, maybe. Right, so here I can bound this by, say, 4 epsilon n.
Is n and not n squared or something?
Yeah. It's OK. It's n. The reason it's actually good that you're pointing this out. So I'm really strongly using the fact that I know that T was a rank n matrix, and I also know that T prime is a rank n matrix, and so their difference couldn't possibly have rank higher than 2n. Yeah, but generically it could be as high as n squared. OK, so by this step we achieve this first requirement. And then what we do is we need to accomplish this as well. But what we're going to do there is we're just going to compute the projection to the span of, or not to the span. We're just going to compute the projection to this set of matrices that have rectangular norm at most 1. Right, so our second step is going to be to let T prime prime be the projection in L2 of T prime to K, where K is the set of matrices with spectral norm at most 1. OK, and because T is already inside K, when I take T prime and I project it in L2 down to K to get T double prime, the distance between T and T double prime can only decrease. So I will continue to satisfy this property. OK, and then we just hand off to Yonnex algorithm in exactly the same way that the sum of squares algorithm did. I guess there are a couple of subtleties. There are many subtleties. So one thing is that this is good enough for getting one component, right? So to get one component, we now spent time. You can verify this later in the privacy of your own home. So So if you do all of the careful analyses of how much time each of these spectral projections took, it will take time n to the omega plus 2, where omega is the matrix multiplication constant, right? So let's pretend that that's 2. So right, so this is like, but the input has size n to the 4, right? It's an order 4 tensor. So this is like nearly linear in the size of the input, but that's only for recovering one component, right? And then you can actually do this like n times, or order n times, and you'll recover 0.9 of the components faithfully. But after that, because we sort of, I mean, here what we did was actually potentially pretty damaging to some of the components, right? And so we have to do a recursion. Actually, that's not different from what the sum of squares algorithm does. But in the sum of squares land, you can sort of add extra constraints to your SDP that say, I don't want to be near any of the components I already found. And we, in the spectral land, can't do that. So that's where the additional complexity that David mentioned in his talk really comes from. But yeah, I guess that concludes. Sorry for going over time. Maybe I'll say one nice open direction is to try to generalize this to the case where your tensor is not orthogonal and you actually have more than n, rank higher than n, right? So to overcomplete tensors. And there it seems like there are some obstacles that we don't know how to overcome yet. Okay, thanks.
If the noise is random instead of worst case, can you find the components exactly?
I think, not that I know of off the top of my head, but you might not need to do the recursion step.
But even the SOS algorithm doesn't find them exactly if the noise is random. We don't know any algorithm.
Yeah, not that we know of, right? Yeah.
So why do you only pull off one component?
Yeah, why do we only pull off one component? So this has to do with what I didn't tell you about applying Yonnex algorithm to the SDP solution. So somehow this condition only tells you that if you look at one component of T, it will be like the SDP solution will be at least like, you know, 1 correlated with it, right? The correlation will be at least 1, and somehow that's the one that you're going to recover in that step, right? So even with the SDP, actually, you have to run this iteratively.
So you find one component has large correlation with T.
Yeah.
Large is like 1 minus epsilon, and you continue.
Right, like when I analyzed Yonnex algorithm over here, you know, I used really strongly that I knew exactly what this slice looked like, and I said, look, here's the SVD, right? But when you don't actually know exactly what the slice is, you have to do something that's, I mean, it's not very complicated, but it's like, you know, you apply Markov's inequality to say there's at least one guy that you're correlated with, and then you actually need the Gaussian to be closer to that guy than to the rest, which happens with inverse polyprobability.
Do you get 1, or can you get like n over 2 or something? Like, can you...
I think you can get 1.
You can really just get 1.
Yeah.
Okay.
I mean, you don't, right? You really don't know why, right? Like it could, I mean, the SDP, I think there's nothing that prevents it from picking one guy to be close to, and then all of the other guys, maybe it just ignores them entirely or something. I mean, I don't know. I mean, you'd have to think about it more carefully, but I think you can only get 1 at a time. Yeah.
So let's see.